Pluto is a distant and confounding minor planet, once considered a part of our planetary group's planetary family. However, recent alarming announcements by leading astrophysicists Neil deGrasse Tyson and Michio Kaku have brought Pluto back into the spotlight with an amazing revelation. They suggested that this chill world is on an impact course with Neptune. Yet, how could this happen, and what might be the results of such a significant event? Are we seeing an intriguing cosmic eccentricity, or is there something else to this approaching limitless effect? Join us as we investigate the conceivable outcomes of a Pluto-Neptune collision. Pluto, a past planet that was downsized to a dwarf planet, is somewhat an enigma due to its odd orbit, and it remains a subject of interest and study in the astronomical community. As indicated by recent expectations by leading specialists, Pluto's trajectory is dangerously close to Neptune's. Neil deGrasse Tyson and Michio Kaku are both raising the alarm about a possible dangerous collision between these two planets, which could represent a critical risk to Earth. How is such an event even possible? Pluto's journey around the Sun is unlike that of any other planet in our solar system. It requires an unbelievable 248 years to complete a single orbit, meaning that since its discovery in 1930, it hasn't even completed one full revolution yet. However, the interest doesn't stop there. Pluto's orbit is marked by its astoundingly curved shape, straying off altogether from the almost round orbits of the major planets. What makes Pluto's orbit even more astonishing is its inclination of 17 degrees to the ecliptic plane. The course Pluto follows is much steeper compared to other planets. One of the most interesting parts of Pluto's orbit is its crossing point with Neptune's. For something like 20 years in each orbit, Pluto actually draws closer to the Sun than Neptune, challenging what we'd expect from their positions in the planetary system. This prompts the natural question: why hasn't Pluto collided with Neptune? The answer lies in the gravitational effects of other planets. The investigation of Pluto's orbit began shortly after its discovery. Initially, astronomers attempted to determine its unique orbit. Unlike other planets whose orbits lie mostly close to the ecliptic plane, Pluto's orbit stood out with its steep inclination and curved shape. The mystery deepened with the realization that Pluto's orbit does indeed cross Neptune's. The stability of Pluto's orbit amidst these complexities is proof of the intricacies of celestial mechanics. The three-body problem in space is about figuring out how three bodies like Pluto, Neptune, and the Sun move and affect each other through their gravity. Pluto's orbit is, in fact, turbulent. Minor deviations in starting conditions can lead to significant differences over millions of years. However, these unusual properties of Pluto's orbit have been found to maintain stability over especially long timescales, keeping tumult under control. Recent simulations have helped us understand how the giant planets like Neptune, Jupiter, and Saturn influence Pluto's orbit around the Sun. Jupiter's massive gravity is strong enough to keep Pluto on a stable path for potentially billions of years. These forces are essential in maintaining the order and consistency of celestial dynamics. Without these factors, our local planetary system would be a place of much more unrest and unpredictability. Pluto's orbit is a remarkable illustration of celestial mechanics at play, displaying both stability and chaos within our local planetary system. The unique characteristics of its orbit, influenced by the gravitational forces of nearby planets, especially Neptune, highlight the intricate and dynamic nature of space. Predicting major events, particularly when they involve turbulent orbits like Pluto's, presents tremendous challenges. The inherent unpredictability of these systems means that long-term forecasts are often filled with uncertainty. While numerical simulations offer a powerful means for understanding and predicting the future behavior of celestial bodies, they also highlight the limitations of our predictive abilities. So why are prominent astrophysicists only now raising concerns about a potential crash between Pluto and Neptune? Despite the various complex forces working to prevent such an event, Neil deGrasse Tyson and Michio Kaku, both renowned figures in astronomy, have expressed concern about a possible collision between Pluto and Neptune. If Pluto and Neptune were to collide, it would be a captivating and devastating event in our neighborhood planetary system. The impact would release an immense amount of energy, probably breaking Pluto, given its smaller size and icy composition. Debris from the collision could scatter across the planetary system, potentially posing danger to other planets and their moons. For Neptune, such a collision could alter its current atmosphere and possibly its orbit, depending on the specifics of the crash. Michio Kaku, a prominent theoretical physicist known for his work in string theory, brings a unique perspective to the discussion as well. His views on the future of space exploration and the connection between celestial mechanics and theoretical physics offer valuable insights into the mysteries of major phenomena like Pluto's orbit. Understanding the complex gravitational interactions and orbital elements of celestial bodies like Pluto can yield important insights for future space missions. This knowledge can help in navigating the planetary system more efficiently, predicting potential hazards, and even planning missions to the outer reaches of our solar system and beyond. The lessons learned from studying Pluto's orbit can be applied to exploring other celestial bodies, providing a roadmap for how we might approach and understand distant worlds. Regarding the physics of planets, celestial mechanics and theoretical physics are deeply interconnected. The movements and interactions of planets, including the gravitational dance between Pluto and Neptune, relate to the fundamental principles of physics. If Pluto and Neptune were to collide, it would be a monumental event in astronomy, offering a unique observational opportunity that could potentially connect with string theory. String theory, a theoretical framework in which the point-like particles of particle physics are replaced by one-dimensional strings, aims to explain the fundamental forces and matter in the universe. The collision could create extreme conditions of energy and gravity, possibly creating circumstances where predictions made by string theory could become detectable. For example, the high-energy impact could provide insights into the behavior of fundamental particles and forces under extreme conditions, a key area of interest in string theory. While the direct effect on Earth would be negligible due to our distance from the outer planetary system, the scientific implications of such an event could be profound, potentially contributing to our understanding of the fundamental nature of the universe as described by string theory and other areas of theoretical physics. Pluto's confounding dance around the Sun continues to enrapture scientists and enthusiasts alike, offering a window into the complexities of celestial mechanics. While its reclassification as a dwarf planet sparked discussion and redefined our understanding of planetary bodies, recent discoveries about its orbit have reignited interest in its role within the local planetary system. Neil deGrasse Tyson and Michio Kaku, two distinguished voices in astronomy, have raised concerns about a potential crash between Pluto and Neptune, shedding light on the complex dynamics at play in our cosmic neighborhood. Their warnings emphasize the importance of understanding the gravitational interactions and orbital mechanics that govern celestial bodies' movements. Pluto's orbit, characterized by its unpredictability and steep inclination, defies traditional assumptions and challenges our view of planetary motion. Unlike the nearly circular orbits of its neighboring planets, Pluto's path follows a unique course, intersecting with Neptune's orbit at points during its long journey around the Sun. The gravitational influence of other planets, particularly Neptune, plays a crucial role in shaping Pluto's orbit and maintaining its stability over hundreds of years. Despite the turbulent nature of its path, numeric simulations and theoretical models play a vital role in predicting the future behaviors of celestial bodies and understanding the complex interactions between planets. These simulations show that, while Pluto's orbit is turbulent over thousands of years, it remains relatively stable within the broader framework of the solar system's gravitational field. The potential for a collision between Pluto and Neptune, as proposed by astrophysicists Neil deGrasse Tyson and Michio Kaku, highlights the ongoing uncertainties and intricacies in planetary dynamics. While such an event remains hypothetical and highly unlikely in the near term, the gravitational dance between Pluto and Neptune underscores the fragile balance of forces that govern celestial bodies within our solar system. Beyond its scientific significance, Pluto's study offers practical insights for future space exploration missions. The New Horizons spacecraft, launched by NASA in 2006, provided exceptional images and data of Pluto and its moons during its historic flyby in 2015. The mission revealed stunning details of Pluto's surface features, including mountains of water ice and vast fields of frozen nitrogen, enhancing our understanding of the geological processes shaping the distant dwarf planet. The success of the New Horizons mission highlighted the technological advancements and collaborative efforts required for deep space exploration. By studying Pluto and its moons, scientists gained valuable insights into the diversity of celestial bodies and the environmental conditions present in the outer regions of the solar system. These discoveries have implications for future missions to explore other dwarf planets and trans-Neptunian objects, furthering our understanding of planetary formation and evolution. Pluto's status as a dwarf planet has also sparked discussions about the criteria used to classify celestial bodies within the solar system. The debate over planetary classification reflects broader questions about scientific classification systems and the evolving nature of astronomical knowledge. While Pluto meets some criteria for planetary status, such as orbiting the Sun and having sufficient mass for self-gravity, its classification as a dwarf planet highlights the diversity of celestial bodies beyond the traditional 8 planets. Studying Pluto's orbit expands our knowledge of celestial mechanics and planetary dynamics to the outer reaches of the solar system. By examining the interactions between Pluto, Neptune, and other celestial bodies, scientists can gain further insights into the formation and evolution of planetary systems. These insights are crucial for developing theories about the origins of our solar system and understanding the processes that shape planetary bodies over billions of years. Pluto's discovery and subsequent study have contributed to our understanding of planetary migration and the formation of the Kuiper Belt, a region beyond Neptune populated by small icy bodies. Studying Pluto's orbit provides clues about the gravitational interactions that may have influenced the formation of planets during the early stages of the solar system. In particular, the interplay between Pluto and Neptune suggests that these bodies were once much closer to each other in the early solar system, before gravitational interactions caused them to settle into their current orbits. Despite the warnings about a potential Pluto-Neptune collision, scientists continue to study Pluto's orbit to refine their understanding of celestial dynamics and improve predictions of future events. Whether or not such a collision occurs, Pluto's enigmatic path through the solar system remains a valuable laboratory for exploring the complexities of celestial mechanics. As our knowledge of Pluto's orbit continues to evolve, so too does our understanding of the broader forces shaping the solar system, inspiring future generations of scientists and explorers to unlock the mysteries of our cosmic neighborhood. Pluto's orbital behavior not only challenges our understanding of gravitational dynamics, but also raises intriguing questions about the broader evolutionary processes of our solar system. One of the most puzzling aspects of Pluto's orbit is its relationship with the Kuiper Belt, a region beyond Neptune, where Pluto resides. This belt is home to a vast number of icy bodies, dwarf planets, and comets, many of which share characteristics with Pluto. This area is thought to be a remnant of the early solar system, and studying its objects helps scientists piece together the puzzle of how the solar system formed billions of years ago. An important theory in planetary science is the notion of planetary migration. This idea suggests that planets may not have always been in their current positions. In the early solar system, gravitational interactions between the giant planets like Jupiter and Saturn could have caused smaller bodies like Pluto to shift or migrate outward. This could help explain the presence of objects in the Kuiper Belt, as well as the unusual orbits of bodies like Pluto. Some researchers propose that Neptune may have migrated outward, pushing Pluto and other objects into more eccentric orbits, while preventing their direct collisions by stabilizing their paths over time. The dynamic interactions between Neptune and Pluto's orbit also suggest that Pluto's movement is governed by complex resonances with other objects in the solar system. These resonances, which are patterns of orbital motion that occur when objects exert gravitational influences on one another, can explain why Pluto's orbit remains stable despite crossing Neptune's orbit. It's fascinating that Pluto and Neptune are in a 3:2 orbital resonance, meaning for every 2 orbits Neptune completes around the Sun, Pluto completes 3. This gravitational lock prevents them from colliding, as their orbits adjust in such a way that the 2 bodies avoid a direct encounter, despite their orbits crossing. Furthermore, the study of Pluto's surface and atmosphere continues to yield surprises that reveal the complexity of this distant world. When NASA's New Horizons spacecraft flew by Pluto in 2015, it captured stunning images of Pluto's surface, revealing vast icy plains, mountains, and even a heart-shaped feature made of nitrogen ice. The spacecraft's data showed that Pluto's atmosphere, though thin, undergoes dramatic seasonal changes due to its elongated orbit. These changes offer new insights into how planetary atmospheres can evolve over time in response to orbital shifts. Beyond its role as a celestial object, Pluto's classification as a dwarf planet continues to spark debate among astronomers. While some argue that it should be reinstated as a planet, others maintain that its small size and location in the outer solar system make it more fitting as a member of the dwarf planet category. Regardless of its official status, Pluto continues to captivate both scientists and the public, serving as a reminder of the complex and ever-evolving nature of our solar system. Looking to the future, Pluto's study is likely to remain at the forefront of planetary science. The discovery of new objects in the Kuiper Belt, as well as the ongoing development of advanced space exploration technologies, promises to uncover even more secrets about Pluto's past and its interactions with the other bodies in the outer solar system. Understanding Pluto's orbit and its place in the broader cosmic framework may help scientists better predict the fates of distant planets and refine our knowledge of how planetary systems form and evolve over time.